Hello everyone, we can start now. Let me know if there's any issue with my mic. Okay. So before we continue the lecture from last week, let me go through like a couple of points. So programming assignment 1 was released last week, and the due date is 11th of October. So I will suggest you like to start working on that right now, because the first part we have already covered, and I released it early so that to avoid like any conflict with the midterm, because you will need some time to prepare for your midterms, which will be I think 21st to 22nd. And the second question for that assignment, I think part of that we'll cover today, and the rest we will cover on Thursday. So that's one thing. The second item is we are going to have a tutorial for that assignment. So for students who are not like very experienced with coding and they might need some help. So what we're going to do is we will arrange one tutorial session for that assignment, and it will happen during the TA office hours. So this is going to happen this week, Thursday, 3 to 4. So if you have any question, any doubt regarding the programming assignment, please join this session. It will be very helpful for you. Okay, so a question from Amelia, will the tutorial be recorded? Yes, the tutorial will be recorded, so it will be available later on web courses. So if you can't attend the office hours, you can watch that video later. And I think that's the same question from Tristan. Okay. The other item I had is regarding GPU accounts, although you don't need them now. But if you need GPU access for your final course projects, and which I think you should need like for most of the projects, depending upon, and I'm sure most of you will select like a deep learning based project. So in that case, you will need GPU machines. So if you are well familiar with this, it's fine. And if you have GPUs, then you can use your own GPUs. We don't want you to force to use these GPU machines. But if you don't have access to GPUs, or you don't want to use like any cloud-based GPUs which are freely available there, so there might be some learning curve for you, how you can use this. So this is like specifically for those students. If you want to start early, we can provide you the username password for these accounts, and there will be a tutorial as well. I mean, we are not going to have that tutorial live this time. We have the recorded video, which will be available on the course website, and you can watch that video, and that will give you like answers to all of your questions, how you can use these GPU machines. And if you have any questions further, of course, we are there to help you. Okay, so I think there's no other question. So those were all the items I had. Any other question before we start the lecture? Question from Connor: do you think 6 GB GPU will be good for programming? For programming assignment, yeah, I'm sure that's fine. I think for the programming assignment, even your CPU is fine. I'm more worried about like the course project, right? And even like depending upon what course project you're selecting, 6 GB GPU might be okay. But if your data set is like too big, then this might not be sufficient. But whatever the case is, you can like familiarize yourself with like how you can do GPU training using your 6 GB GPU, and then you can use that experience on the cluster. Okay. So if there's no other question, so let's continue the lecture from last week, where we were talking about neural networks. So last time we discussed how these perceptrons are actually similar to the neurons in our brain. And the idea was the neuron in our brain, they have dendrites where they receive the signal, right? And similar to that, in the perceptrons, we have these input wires. You can call them wires because you're taking inputs from these wires, right? Similar to dendrites. And then you have weights on these edges, right? So what will happen is each input will be multiplied with this weight, and then you take a linear combination of all these inputs. You can add those and then pass it through like some kind of activation function to decide, okay, what's the final output of your signal. And that's like similar to your neuron, where the main cell body actually takes input as all the activations using these dendroids and then pass the signal through this axon all the way to these branches to the next neuron. So that was the analogy. And so the basic building block is actually the perceptron, the figure I showed you in the last slide. And you can use this perceptron for linear classifier. And the idea will be like you will only need some set of weights, and you can call that like a vector of weights and a bias B. All right. So let's try to understand this. So let's say this is your perceptron, and these are your input values, x1, x2, x3. So in this case, your input has like just 3 dimensions, but of course it can have multiple dimensions as well. So it can be easily generalized. And what will happen is this perceptron will take these 3 values as input, and it's going to generate a binary output. And this binary output is going to say, okay, 0 or 1. So it could be positive, negative, and that's a linear classifier. You take in values and you make a decision. So let's see like how it's done in perceptron. So inside your perceptron, you have these set of weights, and these weights are corresponding to each input signal you have in your data. So if you have like 3-dimensional input data, you will need 3 different weights. And then you will need one additional term, which is called bias. So these weights are actually multiplied by each of these input signals. And then the linear combination is added with this bias value. So we'll talk about like why we need a bias. Now, what will happen is you can determine the output from this perceptron using this simple like equation. So you take a dot product of W and X. Is there a question? Sanjay, if there's no question, can you please mute your mic? Thank you. Okay, so you can, okay, just give me a minute, I'll be right back. All right, sorry about that. Okay, so you have these 3 signals as input, and you can represent this as a vector. So we are representing this as a vector X. And again, we are representing the weight as a vector. So that vector will have 3 different values, and this is like W here. And you know that you can just take a dot product of these 2 vectors, and that's going to give you like x1 multiplied by W1, x2 by W2, x3 by W3. So it's basically just a dot product multiplication of 2 different vectors. And then for each perceptron, you have this bias term, you add that value. Now, what you will do is you will take this value and see that, okay, if this value is positive or not. If this is positive, you say that, okay, you have a positive signal, or you can say that it's a positive sample, whatever you want to classify. And if it's not positive, you say it's not a positive sample. So this is like just a binary classification. So this is like, you can see that a very simple perceptron with few weights here and a bias term, you can easily like develop a binary classifier. That is interesting, and later we'll see like how we can easily scale this thing up to actually create our multi-layer perceptrons. So this I was saying like the dot product, right? You can just take element-wise multiplication and add those values. So that's exactly your dot product. So later we'll see like how this is useful. Now let's try to understand this using a very simple example. Let's say we want to classify an image. Okay, and the image has a resolution of 28 cross 28, and let's say it's a binary, it's a grayscale image. So you have just one single channel here, right? Now what we can do is we can take these 28 cross 28 pixels of that image, and we can create a vector out of it, and that's going to give you around 784 different values. And this input image you can represent as a vector, or you can represent that as a matrix as well. And in that matrix, you only have one row. Okay, so this is a matrix. And then for this kind of input, what you need is you need a weight vector for each pixel location, which means that you need 784 different weight values. And again, you can represent this as a vector, just 784 values, or you can represent this as a matrix. And again, in this case, you can see you have 74 rows and just one column. So the column of that matrix represents your weights. And it's actually pretty interesting why we are representing them as matrix. Later, we will see how that is more efficient. And then later, after these, like we'll have a bias term for each perceptron. So that's just a number. So with this perceptron, if you want to classify this image, we can just take a matrix multiplication of these two matrices. Right, so that's XW, and then just add the bias term. And I mean, you have seen in the linear algebra basics that you can easily multiply these matrices because they're compatible. And the output of these two matrix multiplication is going to give you just one number, which will be 1 cross 1. Because the outer terms are like 1 over here and 1 over here. So basically, this is like you are multiplying the first row of your first matrix with the first column of the second matrix. And again, that's just a dot product. And then you add the bias term. So here you can see that you can represent this whole perceptron using a matrix multiplication. And you can have a lot of optimizations for performing matrix multiplication, specifically like in GPUs. And that was the reason we wanted to represent these as matrices. Okay, so that was binary classification. Now, what if we have more number of classes in our data? So that's pretty simple. We just add more perceptrons. Let's say we want to do a multi-class classification where we have 3 different classes. We can simply add 3 perceptrons. And again, you can see that each perceptron will take input from all the signals, right? And each perceptron will give you one output. And what you can do is you can pair like output of each perceptron to one class. So if you have 3 classes, we'll have 3 outputs, and each output will tell you whether that particular class is present or not. And one interesting thing here is these perceptrons are actually not sharing the weights of these edges. So you will see that in this perceptron, you will need 3 different weights, each for x1, x2, x3. So those weights will be different from the weights which you have in the second perceptron. And again, different from the weights you have in the third perceptron. So which means that if you add more perceptrons, you are adding more weights, which means like you are adding more parameters into your network. So just keep that in mind. That will be pretty useful later on. Okay, so now let's try to see how we can use that for a multi-class classification problem where we have an image, and let's say these images are coming from digits, and therefore we'll have 10 different classes. So we want to determine which digit is present in the input image. So similarly, what we did earlier, we can just create a matrix for the input. And W again will be your weight matrix. So in this case, you can see that it will be 784 by 10. And the reason is because we need 10 class classification. So instead of one output, we'll have 10 different outputs. And B is the bias term for each perceptron. So we have 10 different perceptrons, right? 10 different classes. So we need one bias for each perceptron. That's why we will require 10 different biases here. So you can see that the biases are not tied to the weights. The biases are tied to the perceptrons. So that's what we are discussing now. But of course, we have variations where we can tie the biases to the weights as well. So that's another variations, which is usually not done, but that can also be done. So right now we'll just have one bias for each perceptron, and that will be shared across all the weights of that perceptron. Okay, so if you put all of this together, again, it's pretty simple. That the first step is matrix multiplication, x times w, and then you add the bias terms. So again, you can do the calculations here. This is the first matrix, this is the second matrix, and if you add the biases at the end, this is going to give you 10 different values, one for each perceptron. And then again, you can add like the biases corresponding to those perceptrons. That will give you an output vector with 10 different values. Each value corresponds to one class in your data. So one interesting thing you might have seen here is that the 10 different perceptrons, you didn't have to perform the matrix multiplication 10 different times. You can just put each perceptron as a column in the second matrix. And that was the beauty, like why we wanted to use matrix. And this becomes more efficient. And you can imagine like the other way as well. So right now this is one, right? Which means you just have one sample, one image. But let's say if you have thousands of samples, you can actually put all those samples in this matrix. Then the first element here will be like 1,000, which means like 1,000 different elements or 1,000 different samples, right? And then again, you can still perform this matrix multiplication. And at the same time, you can get output for all those 1,000 samples. Again, this is just one operation of matrix multiplication. And that's why it's more efficient. So we can do some not optimization, but like a convenience, we can say. So because you don't have to worry about biases, and which makes like it more complex. So what you can do is you can always create a fake feature in your input data and assign a value 1. You can always do that, right? Now what will happen is that will add one extra weight, right? Because for each input signal you need a weight. So corresponding to this one, you will have a additional weight. So this is your input signal corresponding to bias, and that weight could be your bias, because if you multiply that weight with 1, it will give back you that weight, right? And it will be added like to the linear combination of all these signals, and that was exactly what you were doing when you were adding the bias. So then you can define your weights as like W1, W2, W3, like these three were required, and the additional bias one. So everything you can club into one vector. You just need to add this one additional signal, input signal. So again, this is not going to change anything. It's still the same formula, but you don't have to worry about biases anymore. It's just like matrix multiplication, no addition at all. So you don't need like addition of bias here. You can just do this dot product between these two vectors. Okay, so mathematically, it's exactly the same thing. Now, that was perceptron and how we can actually use multiple perceptrons to get multiple outputs. Now let's see if we can try to do some kind of composition using these set of perceptrons. So we call that adding layers in your neural network. And in this case, you can see that these are like all your inputs, and you can actually create layers using those set of perceptrons. In this case, we are seeing here 3 different layers in your network. So the first layer has 3 different perceptrons. And again, you add a layer on top of that. So this has 4 different perceptrons, and then the output layer, which has again just 1 perceptron. This will give you the output. So if you think about this, so the first layer, it's fine. We have seen that earlier. But the second layer is interesting because in this case, the input is actually not coming from the input signal. So the only thing which is going to change is the input is coming from the output of these set of perceptrons. And then you can continue this chain. You can create like a neural network with any depth. Okay. I think there is a question. So question from Syed, what was the purpose of adding 1? So Michael Brown answered that bias times 1. So, but let me clarify that. Let me go back. All right. So this is the basic perceptron, right, Syed? So in this case, you have 3 signals as input, and the bias term, it's tied to each perceptron. So if you look at this equation, what's happening is you take the dot product of weights and input signals, that's W times X, and you're adding the bias, right? And if you carefully look at this dot product, the equation on the right, so again, this is nothing but multiplying the weight with the signal value and then adding those over. So basically it's just W1 times X1 plus W2 times X2. So what we're going to do is, if you just put a coefficient of 1 in this B, then we can actually club this B with the weights W and that 1 with the input signal X. And that's exactly what we did. We added one dummy input as 1 here, right? And then we can easily club this B with the weights. So then we don't require this addition here. And that's why the equation reduced to just the dot product of weights and the signal. Okay, so you don't have the addition of bias term because you added it over here. Okay, great. So, okay, so that's called composition. And it's kind of each layer in this network is representing some function, because essentially, I mean, you have some input and then you're getting some output. And I showed you those equations. That was just linear combination, right? Then you can say that that's essentially a function. And now each layer is a function. Then if you're adding more layers, you're like just trying to compose the functions on top of another, right? To create complex functions. So these are like smaller functions. When you combine them, it's creating complex functions. Okay, so the output of like each function or the set of perceptrons will be treated as input to the next layer or perceptrons of the next layer. Okay, so a question. So I don't know whether this is a question or a comment. So Zubin, I don't think like we added one for binary classification. It has nothing to do with binary classification. So if you still have doubt, please put your question here.
Professor?
Yes.
So I wanted to ask that why do we need bias at all? I mean, can't just weights learn the underlying pattern?
Okay, so I think that's a very, very good question. And let me go back to the architecture again. So if you look at this figure, so right now we just have single perceptron, right? So let's say if you have multiple perceptrons, then sometimes what will happen is if one of the signal is too high, let's say this value is close to 1000, right? And this value is close to, let's say 1. So then we don't want like any of the signal to dominate the output, and that will essentially happen because this is just a linear combination. So to address like those kind of issues, if we add bias, then what we are saying is that even if there are like some kind of discrepancies between the input, then we can try to learn some bias so that we can control like the final output of the network, because essentially we are not going to just have one perceptron. It will be combination of these. So it's kind of trying to balance different perceptrons or whatever activations we are getting out of those perceptrons using these bias terms.
For controlling the impact of this varying range of values of input, we can normalize the input values to be
Right.
in a closer range.
Right. You can vary that, and you can vary that, but again, what weights you will learn on these edges, you can't control that, right?
Right?
So what output you will get from each signal, I mean, that will depend on the weight you are learning.
Okay. Right.
Right. So that's kind of a high level intuition, but again, I mean, it's an ongoing research, and sometimes when if you don't use bias and you use bias, I mean, we don't see like a lot of difference there, right? But by default we do use biases.
Okay. All right.
Right.
Thank you.
So that was like one intuition why we need biases, and there are a lot of others as well, but I think that should be fine for now. Okay, so you can actually just, if you try to relate that bias term with the actual bias you have in real world, right? So bias means if you are inclined towards something. So we are trying to do similar things for the neuron. If we want them to be like inclined toward like some kind of output. Okay, so that's like the intuition. So let me.
Just a quick comment. So if we are assuming that the neurons or the nodes are learning individual features, then we can say that we are giving higher weight to some features and lower weights to some other features by using this bias for achieving whatever goal the network is designed for.
Yeah, but we can't control the learning at that granular level, right?
Yeah, that's what the network is doing on its own.
Right. So we are just trying to facilitate, like providing the network a capability so that if there's a need to learn a bias, the network should do it. So it's just like facilitating that. Okay. Right. Just adding one capability. And if bias is not required, the network will just learn one. Right.
That's amazing.
And then you can, or zero, you can just ignore it. Right. But at least you have that capability there.
That's amazing. Thank you.
Okay. So this is fine. And so now once you have these set of layers, so these layers and the weights you have and the weights and the biases you have in these layers, they will define your network architecture. Right. So when you're saying that you have developed a neural architecture or a multi-layer perceptron, then you are essentially saying that how many layers you have, how many neurons in each layer you have, whether you have biases or not, what's the dimension of the input, what's the dimension of the output. So all those properties actually define your architecture. So in this case, we have two layers. The final one is the output layer. And you can see that, okay, first layer has 3 neurons, second layer has 4 neurons, and that's all we need for defining it. Okay, so these are your inputs. You can have multiple inputs. That's the hidden layer 1, that's the hidden layer 2, because these are like intermediate layers. That's why we call these hidden layers. And sometimes when you can call this as input layer as well, because this is taking like input from the data, and this is called output layer because this is giving you the output. And as I said, like it's all about like matrix multiplication. We saw that earlier. All these operations are taking like linear combination of the input features and propagating them to the next layer. All of this can be done using matrix operation, and GPUs are we have like very optimized code which can handle large matrices, and that's why training these networks is pretty easy and pretty fast. Okay, so I have a pop quiz for today, and this is based on what we just discussed. Okay. So the question is, we have a neural network and you have to determine how many parameters you have in your network. Okay, so let me explain like what parameter means. So if you have a perceptron where you have a weight vector which has 10 values, which means you need 10 different weights, and you have one bias, so then that will amount to 11 parameters. All right, and similarly, if you have two such layers, you will need 22 parameters. So any question on like what network parameters are before we continue this? All right, so then the question is, your input feature, which is going to the first layer, it has 50 different values, right? And then you have the first hidden layer, and I think that's the only layer you have, and it has 100 neurons. All right, so these 50 values are sent as input to these 100 neurons, and then you're performing a 1000-way classification problem. So you will have 1000 different outputs. So the question is, how many network parameters you will need for this? You can take like 30 to 45 seconds, and you can put your answer on chat box, but send that as private just to me so that others are not able to copy your answer. If you're doing it public, then it's fine. There will be no deduction, but again, others can see your answers. So when you reply, just I think if you select like to just me, there's an option drop down menu there. So question from Fernando, bias are for each layer. So you need like one bias for each perceptron. Okay, so question from Sadia, can you repeat features, please. So features, it's like your input data. It could be image or it could be anything, but whatever that input is, it has 50 different values. So is it clear, Sadia? And I think there's another question from Lawrence. Did you say 10 weights plus the bias is 11 parameters? That's right. If you have 10 different weights and one bias is in a perceptron, that will amount to 11 parameters. And you don't have to do the full calculation. If you just give me the equation, that will be perfectly fine. So we are not like looking for your mathematical skills. It's just like your understanding of this concept. So question from John. There will be no poll, so it's just a quiz. Just put your answer like in the chat box and send me as a direct message. So Victor, you can put the equation, that will be just fine. You don't have to do the full calculation. I think most of you are missing, like you need 1,000 outputs. Don't see a right answer yet. Okay. So I think that's enough time. So let me put this message here just to mark as end of this block quiz. All right. So if you're a few seconds late, don't worry, I will count that in. But it should not be like after I have showed the answer. So the answer is like 100,000, 106,100. And let me like go through this, how we got this number. So input feature has 50 different values, right? And then you have, you will have like one bias for each perceptron, right? So you have 100 neurons here. So you can just club this one with the input here. And again, you can have a bias like in your input. So it's equivalent. So this will give you roughly 5,100 neurons. And then if you look at the output here, so in this case, this layer will have 100 neurons. And then you can add one for the bias. And again, you need 1,000 outputs for the classifier, right? Because this will have 1,000 different classes. So if you just do the math here, we'll get this number. So any question on this, I can go through this again. So let me see if there's a question. Okay, so I don't think there's a question, but if you have any question now, just let me know. Yeah, I think there is a question from Tristan and Sean and James. So is this graded? Yeah, this will be graded, but again, this is pop quiz, so these are like bonus points. If you're wrong, don't worry. So this is like on top of your 100%, which you are going to grade it upon. And each pop quiz is like roughly half of your homework. Okay, and this is like either true or false. I don't think there will be in partial credit. Okay, so that's fine. If you forgot bias in the equation, I think you should be not given partial because it's saying don't forget to include bias. Okay, anyways, so that's fine. Let's continue. We have to finish this and also start the convolutional neural network, which is more interesting. Okay, so now let's see like what's the problem with this kind of neural network. Now what we have done is we have formed chains of linear functions, right? Each layer is a function because that function is taking some input, producing some output. And then you're linearly combining these functions on top of each other. Now, if each of this function is linear, which we know it's linear because it's just linear combination, then it doesn't matter how many functions you put on top of each other. It doesn't matter like if you have a very long chain of linear functions, at the end, it's just going to be a linear function. You can do that approximation, right? So if G is a function and it's a combination of F and H, which are linear, then again, this function G can be approximated as a linear function. You don't need actually two functions for those. Okay, so even if you have 100 layers of this neural network, it will just be like a single function. Okay, so that's problem number one. Now let's try to understand how that's actually true. We can actually go through these equations. So if this is your neural network with three inputs, this layer and then output, so you can represent that using Z1, that's your weights, W1 for the first layer, right? X is your input and B is your bias. And Z2 will be again these weights from the second layer, and Z1 is coming from output of the first layer, and then you add biases. So this is pretty simple, right? So, and this Z2 is your output. So this is like two-layer neural network. Now, what you can do is you can actually put the value of Z1 in this equation. And you know, this Z1 is over here. So this is your Z2. So if you replace Z1 with this equation, and if you try to simplify this, so this will be like multiplication of these two weights. And again, you can multiply these weights. So that will again be like just one matrix for weights. You can name that like give that a new term. It could be just W, but you have X over here. And again, this one, you can see that these are your weights. You can multiply with just biases, and you have more biases, and adding all of this will just give you a bias. Right? So you can see that you can reduce this kind of architecture again just into like single layer. It's the only difference is the weights which you have here. So these weights are different and these biases are different. But again, when your network can learn those weights, right? It's just linear. It can learn any weights. And of course, you can factorize like this matrix into 2 or 3 as well. So that's the idea. I mean, if you don't have nonlinear functions, if you just have linear functions, it doesn't matter if you use 100 layers or 2000 layers. It's still going to be a single layer approximation. Okay. So the second problem is, and this is, I think, somewhat relevant to what Momal asked about biases as well. Not exactly like that issue, but somewhat relevant. So what will happen is right now, the neural network we developed, the output was a step function, right? We use a threshold. We say that, okay, if the value is greater than, let's say, 0, positive, then we say that, okay, that class was present. And if it's negative, we say that class is not present. So you can see that your network is a linear function, right? If it's a function, then it's going to give you a continuous range of values as output. It's not going to be discrete. So what that means is your network will output value 0. It will output like values very close to 0. It's going to output values maybe -4, -3, and -2, right? And again, some positive values as well. Now, if you think about this, what's going to happen is if your network predicts, let's say, -0.1, so it's close to this point, then you're saying that class is not present. And the second sample, if your network predicts 0.1, then you're saying the class is present. So if you look at the difference in the output of the network, just forget about the classification. Just look at the value. So that value is like from -0.1 to +0.1. So that's like just a change of 0.2. It's a very small change, right? And then that small change is actually changing your network's output. It's going from being not present to being present, which is pretty huge. Because if you have a network prediction which is -4 and the other which is +4, that's a huge jump. You can say that, okay, classes maybe not present and present. You can make that decision, but this is kind of dicey. So that's a big limitation of linear classifiers. And what's happening here is if you change your input with a very small amount, right? Let's say 0.1, 0.2, the output of your network, which is kind of binary, it's changing drastically. It's changing from class being not present to class being present. So we don't want that. So this is also called like Heaviside function. So what we want is if the input is changed like with a very small value, let's say delta W, then the output should also be changed with a very small value, delta output. So how we can do that? We can actually introduce non-linearities into the network. And the way we do that is we have activation functions. So what we do is we take the output of your perceptron, which is this linear combination, and we add the bias, and then we whatever output we are getting, we send it to a activation function. So this activation function, I mean, we have a lot of activation functions. So one example is sigmoid. What it does is, if you given a value like from negative infinity to plus infinity, it will first of all, it will squish the values of the output between 0 and 1. So the output of the sigmoid function is never going to be greater than 1. So it's capped at 1, and it's never going to be negative value. So that's like another positive side, that you're kind of controlling your values. And later we will see that why that's important. But that's one benefit. The other benefit is you are introducing this non-linearity. So this function is not linear, right? So if you take like some step in x direction, the step in y direction will depend upon where exactly you are located in your x-axis. So if you're very far away, like towards the right, then even if you take a very huge step in the y direction, you're not changing much, because you can see like it's kind of saturating here. But if you change like a very small value close to this region here, then you are changing the y value by a significant margin. And that's why it's non-linear. And if you use this activation on top of this, it will introduce that non-linearity into your perceptron as well. And that's like a equation of this curve, which is fine. Okay, so we have different kind of activation functions. We'll just skim over those, and later we'll discuss like why we need different kind of activation functions. So what we do is we get the output of this perceptron and send it through the activation, and whatever value we are getting, that is called the activation of this particular neuron. So sigmoid was an example. 10H is another interesting example. So in this case, sigmoid was capping between 0 and 1. 10H is capping between -1 and 1. And again, you have a nonlinear function here. And we have a very interesting activation function. This was introduced recently into deep learning. So this is kind of, if your value is positive, it will just retain that value. It will not change it. It will still be linear. But if it's negative, then it will make it 0. So by doing that, you're trying to introduce nonlinearity. Okay. So let's wrap this model up, and we'll quickly move to CNNs. So this is like well grounded in theory, which is good. And essentially what you can do is you can represent a NAND function, right, using any binary function. And then you know that you can use these like NAND functions in different compositions to actually generate many other complex functions. So that is pretty interesting. Then the other thing is, like, if you have enough number of parameters, right, sufficiently large number of parameters, so ideally you can approximate any function, which is pretty interesting, right? Which means that these networks can learn anything. So, and again, this perceptron neural network, it's not new. So the first neural network, like this is the hardware for that, it was built in 1960. So this was named a Mark I perceptron, and it's pretty old, and there was a lot of controversy, I think, during that time. You can check the wiki blog for this. It's pretty interesting. So in this case, we had 20 we had like 20 cross 20 pixel camera feeds. You can see that like it's just 400 pixels, right? And today 400 pixels is like nothing. So we have those camera feeds like as input, and then they were like these physical weights actually. Right now, I mean, what we do is we have the neural network like into our computers, right, as a soft machine, not a hardware. So we can emulate like those into the network chip, but this was the actual hardware. And you can see like how huge this was, but this was like the first perceptron build. So So another interesting aspect of this perceptron model is, as I said, like a single layer, if you have sufficient parameters, it can learn any function if you have enough parameters. But still, mean when we develop these neural networks, we don't use just single layer. We want to go deeper. We want to have multiple layers. And if you try to understand like why we need that, we want to make use of the power of composition, because how complex your function is, however complex your function is, you can also break that down into like smaller components, right? For example, we were talking about NAND gates earlier, that you can use those NAND gates to actually derive complex functions. So NAND gate is like a very basic function. Similarly, we can actually learn very smaller functions in forms of like those layers. And then what will happen is, if you have like stack of layers, you're trying to reuse those functions again and again. So that's called composition. And if you do that, then that reuse is actually trying to bring that requirement of number of parameters down in your networks. And that's why we need multiple layers. And of course, we can just have single layer and learn it, but that's not efficient. Okay, so now if we have like a multi-layer neural network, so can have multiple layers, and if you have non-linearities in between using activation functions, that is called multi-layer perceptron. This is also called like feed-forward network, a synonym, but you might have heard like MLPs a lot. Okay, so yeah, all these are fine. We want to, so the goal is like we want to build a classifier which can represent various different complex functions. And again, those functions will vary with the problem. And the main idea is like we want to learn the distribution of the input data, right? And at the end, we need like a very good representation which can be used to solve any problem on the data we have at hand. So let me give you a very quick example of MLP when it was used for doing digit classification. So we have a data set called MNIST, and this data set is about handwritten digits. So some samples are shown here. You can see that like different variations of this digit 0. And this has roughly 60,000 images. So 10,000 testing, 50,000 training. So this work was not recent, this is 2010. And they developed a 6-layer multi-layer perceptron, right? And the number of neurons in each layer are specified here, like starting from 2500, then 2000, 1500, 1000, and finally 10. So 10 is like one for each digit class. So you have 10 different digits. That's why it was 10-way classifier. And the performance of such a network is like 99.65%, which means that, so you can see that you have 10 case testing samples, right? So which means that only 35 of the images were misclassified out of these 10,000. So this is pretty good. And I think there's a question from George. Even before that, okay, so that we covered. So George is asking, is a deeper network or wider network better? And that's a very good question. And again, it depends, and that's the open question. And sometimes wider network may perform better, sometimes deeper may perform better, but a combination of those two has always shown to be better than the other. And again, it depends, like when you're saying wider, like how much wide? Is it like just single layer and a lot of neurons? Of course not. But if you're saying that, okay, few layers and maybe more number of neurons, so that might work better for some cases. And I think later when we study CNNs, I think we will cover this aspect. So because there are different variations, like when we need wider networks and when we need deeper networks. So, but I think for now, I might have answered your question, but we're going to cover this later on. So George, just remind me if you forget to cover. Okay, I think it will be better to answer this when we have talked about CNNs. Okay, so that was one simple example of MNIST. So now the question is, if like these MLPs can perform that well, then why exactly we need convolutional neural networks? And that's the topic for the next lecture. So if you think about neural network, these are fully connected layers, right? First of all, you need some kind of features as input, and these features, they can be handcrafted features. Okay, they can be just pixel values. So if they are handcrafted features, it means that we need some kind of domain knowledge or some kind of domain expert, right, to get those features. But if you just want to use pixel values or images input, we have some limitations. So for 28 cross 28 image, it's fine. We'll just have 784 pixels. But if we try to use like a high resolution image, for example, if we have a 256 cross 256 RGB, which is a very common like size these days, it's not huge. So if we use each pixel as a feature, then this is going to give us around 200K dimensional feature vector, which means that for the first layer, you will need that many neurons or that many weights for each perceptron. So that many weights, it's pretty hard to fit in your memory, even if you have bigger GPUs or bigger machines. And so that's just one reason. But the other reason I think we discussed when we started talking about image classification, that why just using image pixels as features is not a good idea. So that's another reason. So, but that's fine. But this reason, how we can resolve this is we can use CNNs. And of course, there are many other reasons on top of that. That's just one reason which I think we can easily understand at this point of time. So CNNs, actually what they do is, in this case, you move from features to features, right? You create features, and these are just feature vectors. In this case, instead of flattened features, we move from volume to volume, right? So you can consider your input image as a volume. So the depth is 3, and X and Y is the resolution of the image. And then again, we'll try to extract features. We'll create another volume, and finally your output. So it's going from volume to volume. And the benefit is when we move from this volume to this volume, we are doing some kind of filtering, which we're going to cover sometime later. Don't worry about that. And when we do that filtering, we do a lot of sharing. So we share those kernels. And that's why we don't need a lot of parameters. In this case, as I said earlier, right, we were using different weights for different perceptrons and different weights for different inputs. So there was no weight sharing happening. And that's why we require that many parameters. So in this case, we are doing weight sharing. So that's a very big distinction between neural networks and CNNs. And I think that's all I have for a neural network. I think we'll move on to CNNs now. We have some time left, but if you have any questions before that, feel free to ask.
I have a quick question.
Yes, go ahead.
If neural networks are basically just estimating some function from the data, would you be able to take